So we've seen how to do this with plug and chug approach. We've seen more circle, but I would like to propose a different approach. One that is more mathematical, slightly, one that uses linear algebra. So we can use a transformation matrix here, T, and again, this only applies for a plane stress state. So we can actually rotate in 2D using a rotation, or what we're going to call a transformation matrix. So we are going to create our new coordinate system here using this linear algebra format. Now, it's important to note we can't use our full not 3D, but our full second rank tensor. We have to convert that into a single column with 3 rows. So as opposed, this is our 3 by 3, this will be 3 rows, 1 column. So you have to do that to make, obviously, the linear algebra work. But we could kind of transform our system here. So we could actually get everything that we want using kind of this formalism. So let's try to answer those questions that we posed previously. So, for example, I want to, and I can look at, this is my stress state, but I am actually going to pull out only the 1, 1, the 2, 2, and the 1, 2 components. So I'm going to make it that 3 by 1. So if I do, for example, stress 1, 1, 2 / matrix form, you'll see something like this. So we're good to go. We've transformed it completely. Remember, it's normal shear stress. Now, let's go ahead and let's start to ask ourselves the question, so what is the rotation to get to that principal stress state? Well, if I do T dot stress 1, 1, 2, if I do matrix form, you see that I get 3, again, this would be my sigma 1, 1 right here. This would be my sigma 2, 2. This would be my sigma 1, 2 prime. So if I'm in my principal stress state, I know that this value, the third equation here, needs to be equal to 0. So I could pull out my third equation. Oops, let me just wrap that. If I pull out that third equation, I can now solve for when does this equal 0 in terms of theta. And I could do that numerically, but not a b, an n. And you see I get 4 values. I get 4 values because of circular symmetry. But I'll pull out one of the values. And again, they're all related by 90 degrees. And this looks familiar, right? It's our same angle that we had in the last 2 videos as well. And we can actually go up and check. Look at the angle here, 19.329. Same exact value. Excellent. So if I were to actually T dot stress 1, 1, 2 / dot theta goes to this angle, we can now see 16.4 would be my normal stress, which is the same one that we've found previously here. 16.4, 3.59. You can see that right here. 16.4, 3.59, and then our shear stress is effectively 0. 10 to the minus 15th is nothing. So we got it. That's it. So that is our angle to get to principal stress. This is our sigma 1, our maximum normal stress in the principal stress state. This is our sigma 2. We can also find out T dot stress 1, 1, 2. If we look at that third equation, if I want to maximize my shear stress, well, I'm just going to take the derivative of this expression with regards to theta, and I'm going to solve when does this equal 0? If I want to find my maximum shear stress state. Because again, it's just a function, and I want to maximize it. So I'm going to do x plus n, and I could pick out a value here. Minus 25.6, where does that look familiar? And we kind of did that previously in the past video as well. So we have that value, and I can go, excuse me, where am I at? I got lost. Actually, but here I am. I can now do, again, T dot stress 1, 1, 2 / dot theta. This is just replace theta temporarily with this value. Oops. This is minus 25. And you see we're at the center of our Mohr circle, and then our maximum shear, 6.4, That value looks familiar right here. And finally, if I want to do what is the stress state, t dot stress 112 slash dot theta goes to minus 15 for that clockwise rotation. This is my new sigma 11. I'm going to copy this and paste it over here. This is my new 12.33, 7.66, 5.96. We got it. All the information that we worked through and how we had to draw circles or plug and chug randomly, this is much more intuitive. Look at there's only you only need a couple lines of code to calculate this. So I would strongly recommend try to get familiar, try to get comfortable with our linear algebra approach. And you can do the same thing for strain as well. So that's fantastic. And next time we are going to get into pressure vessels, which is at the current recording of this video, very relevant considering the really unfortunate disaster that happened with basically the pressure vessel that tried to explore essentially the Titanic wreck. So we'll talk about that next time. See you then. Bye.